Okay, so this is the second and last lesson in thermodynamics. I just want to review that we've already done a lot with thermodynamics previously in the year. In calorimetry, we used Q equals mc delta T. Then we did Hess's Law 1, where we added reactions. You took the two reactions, that's where you had a catalyst or an intermediate that was formed, and you got a final reaction. Then we did Hess's Law version 2, where we did sum of the products minus sum of the reactants. And this is where we used the appendix in the back of the book and we looked up delta H. And then we also did bond energies when we got to bonding. And remember that bond energies, it's bonds broken minus bonds formed. So in this one, you need to remember that this is always going to be the sum of the reactants minus sum of products. Okay, so that's the only one that's kind of backwards. Now we're going to talk about delta S, which, as you recall from the first lesson, has to do with entropy and disorder. And this is going to be in the appendix as well, and it's listed as joules per Kelvin. Now note this value is usually given as, like I just said, joules per Kelvin, and you typically have to convert it to kilojoules per Kelvin. There's several ways to calculate delta G, which is our free energy. The most common is using delta G equals delta H minus T delta S, which I spoke to you about in the first lesson. The other way is sum of the products minus the sum of the reactants, again using the appendix at the back of the book. And then we have two other equations. One is delta G equals negative N F E naught. And we're not going to cover that one until the next unit when we talk about redox. And then the last one is when we have an equilibrium constant, we can use delta G equals negative RT ln of K. And if you recall from the other day, I said that R is 8.3145, and this is in joules per Kelvin dot mole. So we usually need to change units when we use that formula. I typically change my kilojoules to joules to match my R, but if you want to change your R value to kilojoules, then that's up to you. All right, so let's look at a sample problem here. Calculate delta H, delta S, and delta G for the following reaction. So you have to be able to do all of them, and it's really just straightforward math. The biggest thing that I can say is going to be a problem is if you do not watch your signs. If you have a negative sign, make sure you're doing, parentheses and all that. All right, so I'm going to look these up in the back of the book. First, I'm going to look up my delta H values. I'm going to rewrite the equation down here so it's a little bit bigger. So I have 2 SO2 plus O2, and that's going to 2 SO3. So in the back of my book, I've got delta H naught, and that has a value, SO2, of negative 297. I'm looking all of these up ahead of time so that I am prepared. My oxygen is going to be 0. Why? Because it's in the free state, and negative 396 for the SO3. Now, remember your delta H is in, this one's in kilojoules per mole. And now I'm going to do delta S, which is our entropy, and that's going to be in joules per mole. And these all are Kelvin temperature. So SO2 is going to be 248. I do have a value for oxygen gas entropy, because we know gases have the most disorder, and my SO3 is 257. So now that I have all the values that I need, I can actually start solving these. So let's look at delta H first. So if I'm solving for delta H naught, remember it's going to be sum of the products minus sum of the reactants. So sum of P minus sum of R. So I'm going to have 2 times negative 396 minus 2 times negative 297. And when I do the math on that, I'm going to get negative 198 kilojoules per mole. So that's my delta H. Moving on to my delta S, also going to be sum of products minus sum of reactants. I'm not going to write that again. I've got 2 times 257 minus, now I've got 2 reactants, 2 times 248 plus 205, because I only have 1 oxygen. And then on that I get negative 187. Remember, this is in joules, so I need to change that to kilojoules. So joules per Kelvin dot mole. So if I change that to kilojoules, divide by 1,000, I'm going to have negative 0.187, and that's going to be kilojoules per Kelvin dot mole. Okay, so I'm going to do the last one on a new page as I was running out of room. So in the last one, we had to calculate delta G. So delta G equals delta H minus T delta S. So I'm just going to go back and retrieve the answers to delta H and delta S. So we said delta H was negative 198, and our temperature, although it doesn't give a temperature here, you can assume that it is room temperature. So that would be, just want to make sure I have this right, 298 minus 273. So 25 degrees Celsius. So if they don't tell you room temperature is 25 degrees Celsius, which would make our Kelvin temp 298. And our delta S was negative 0.187. And the reason being is because our delta H is in kilojoules per mole, right? And our delta S is in kilojoules per mole dot Kelvin. So these are all both in kilojoules per mole dot Kelvin. So delta G is going to be equal to, and I did this twice, so I believe I did my math correctly, negative 142.3 kilojoules per mole, because we have temperature in Kelvin. So what does that tell us? It tells us that our delta G is negative, which means that the reaction is spontaneous. Okay, let's move on to another problem. Okay, so in this example, we're looking at the Haber process, which is the formation of ammonia. And it says where delta G equals negative 33 kilojoules per mole of N2 consumed at 25 degrees Celsius, calculate the value for the equilibrium constant. So a couple of things going on right away is I notice that I've got kilojoules per mole, so I'm going to want to change that to joules. So right away I know that I'm going to have negative 33,300 joules per mole. And we're going to use the formula delta G equals negative RT ln of K, because it's looking for the equilibrium constant. So I'm going to simply substitute in negative 33,300, and that's joules per mole, equals negative 8.3145, and that's joules per mole dot Kelvin. And my temperature is 25 degrees Celsius, so that's 298, and then I have ln of K. So I divide both sides, and I get the ln of K is equal to 13.44. And then I just take the inverse of the natural log, and I get K equal to 686,780.39. So there's no units for K. K is very large, so we know that it's going to favor the product side. And also, because we started with a negative delta G, we know this reaction is spontaneous. All right, let's take a look at the last problem. Calculate the value of delta G for the following reaction, and they're giving us concentrations. So as soon as I see concentrations, I should be thinking equilibrium expression. So I'm going to do that first. I've got K equal to the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. And then I'm simply going to plug in my concentrations. So I've got 2 squared over 3.01 times 1.25 cubed. And that's going to give me 0.68. So that is my K. So K equals this. So then on the next page, let me just add I'm going to start with K, and I have delta G equals negative RT ln of K. So we're finding delta G. I know my R is negative 8.3145, and that's joules per mole dot Kelvin. I know my temperature is 389 Kelvin. 389 Kelvin, and I need the ln of 0.68. So when I do the math on that, I'm going to get delta G equal to negative 1247 joules per mole, because this is going to cancel. And if I want to report that in kilojoules, negative 1.25 kilojoules per mole. And we also know that this is spontaneous because delta G is negative. All right, that's it for chapter 17.